We sat in the observatory's basement, surrounded by cables, old hard drive cases, and thermoses of long cold coffee, simply trying to prove that a bug is a bug, that the universe can't suddenly start acting as if someone had pulled it over the edge. It all started with the same routine we've been doing for years, comparing new optical maps with archives, the VLT, Subaru, several ESO telescopes, 10 years of observations, thousands of fields, billions of stars. The main project was tediously grandiose, refining the proper motions of faint objects, statistics, galactic dynamics, all this beautiful mathematics which is then transformed into dry graphs for articles. The script that ran the comparison was old, tried and tested, rewritten hundreds of times. We trusted it more than ourselves. If it said a star had shifted by a micro arcsecond, we believed it without question. But that night, it showed not a micro arcsecond, but a milli-arcsecond, and then another, and another. And not for just one star, but for dozens at once. At first we thought it was a calibration defect, oblique flat fields, erroneous accounting of atmospheric refraction, chromatic aberrations, anything but reality. We turned off all automatic corrections, returned to the raw footage, and began manually recalculating the coordinates. And the more we calculated, the colder it became inside. Some faint stars did indeed crawl across the sky, slowly, almost lazily, as if nothing special was happening, but their trajectories were too regular, too consistent. If we extended them years into the future, they would intersect at the same point. We ran the extrapolation using different models and ran several independent codes to repeat the calculations. The results remained unchanged. I remember the moment when someone almost whispered, "Do you remember that in a couple of years, there will be Atlas there?" The room became so quiet that you could hear the hum of the air conditioner. Atlas was already an obsession, a constant throb in our minds, an interstellar wanderer, the first one that could be tracked for years, not weeks. Its orbit had been calculated down to the last detail. In a few years, it would pass through the exact patch of sky where our crawling stars converged. We laughed at first, calling it a coincidence, but then we started checking it seriously, and it was no longer a joke. We used Gaia data, old catalogs, and retrospective images from less sensitive telescopes. If the shift were an artifact, it would disappear into the noise, but it didn't. On the contrary, 10 to 15 years ago, the movement of some sources could be detected even in the old data. We simply weren't looking at them for the right reasons. The most terrifying thing was that these stars didn't belong to any single cluster. They were at different distances, in different directions, but in the sky, they were all crawling toward a single point. In three-dimensional space, their trajectories didn't intersect. But from Earth, the entire picture converged, as if someone had run a finger across the dome of the celestial sphere and gently indented it. Someone suggested using ALMA. Technically, the task was outside its core competencies, but we had enough connections to persuade colleagues to dedicate a few nights to our madness. We drafted a proposal to make it look as respectable as possible, analyzing local variations in the cosmic microwave background, searching for unknown sources near the future trajectory of 3i Atlas. The paperwork looked dull. What we had in mind was quite the opposite. When ALMA first looked into the region where our creeping trajectories converged, I sat in the next room staring at the screen without blinking. The raw spectra grew softly on the monitor. The noise trembled like fog, and we expected anything but what we saw. Against the expected uniform microwave noise in the millimeter range, a narrow peak suddenly appeared. Too narrow, too pure. Powerful, but as if compressed into a single stream. A radio beam emanating not simply from a region, but from a tiny angle. So narrow that if scaled down to Earth, the beam would hit a human pupil from a distance of thousands of kilometers. There shouldn't have been anything there. No known quasar, no active galactic nucleus. We checked every catalog. Our beam appeared as if from nowhere, right at the spot where the comet should have appeared years later. In the protocol, we carefully wrote, "A narrow beam radio signal of unknown origin detected." In reality, the discussion was quite different. Some were shouting about a man-made source, others about an unusual lens, and still others about a software glitch. I sat in the corner and thought of only one thing. If 3i Atlas was still far away, but the beam was already here, then who was actually moving toward whom? It was then that the hypothesis that would later become the center of the entire scandal was born. That the comet wasn't simply flying through the solar system, but was pulling the local structure of space along with it. Not in the sense of simple gravity, but like a hook embedded in the fabric of coordinates. Imagine a map drawn on a rubber sheet. The stars are the dots on it. If you simply drag a single dot, its line of motion remains narrow and local. But if you grab the edge of the sheet and start dragging, the entire image slowly shifts, and the dots that appear to be moving along your dimensions are actually simply following the deformed grid. Our crawling stars might not have been fugitives, but victims of such a deformation. The celestial coordinate grid was slightly bent toward the future position of 3i Atlas, and the stars obediently floated along, not in reality but only in our observations. But if the coordinate grid is changing, then so are we. We started digging deeper. We refined the parallaxes, checked for systematic errors, and looked for shifts in other ranges. We incorporated X-ray and infrared data. We tried to figure out whether this was a shift in the optics, the atmosphere, the equipment, or something truly in the celestial sphere. At the same time, repeat observations were requested from ALMA. The millimeter wave beam hadn't disappeared. Moreover, it lived by its own rules. Sometimes it brightened, sometimes it dimmed, sometimes it split into several subpeaks, as if an internal modulation were emerging, but most importantly, it always remained aligned with that same point. One day, we decided to test the beam's stability over time. We compared its direction with the Earth's orbit, the Sun's movement through the galaxy, and the predicted trajectory of 3i Atlas. The results were strange. From an outside observer's perspective, the beam seemed attached not to the comet or some distant galaxy, but to our entire system. It shifts so that it will perfectly align with the comet's position in a few years, but it also takes our movements into account in advance, as if someone had already mapped out the route using predicted coordinates. At some point, we realized we'd stop discussing whether this could happen. We were already trying to figure out who was doing this and why. Officially, they were still writing cautiously. However, within the team, completely different formulations began to circulate. Someone called the beam a traction channel, another an anchor. One of the theorists, slightly out of his mind, called it a sling by which a sector of the local metric is pulled. When they brought in people studying general relativity, the situation became even more troubling. They constructed several crazy models in which such a radio beam could be a side effect of a deeper operation, something like a local reconfiguration of the curvature of space. In these equations, 3i Atlas looked not like a lump of ice, but like a marker, the boundary of the working zone, the edge of that very rubber sheet being pulled. But somewhere around this point, it wasn't just our colleagues who noticed us. People in suits who never introduced themselves by name joined the project. They very politely asked us to sign additional non-disclosure agreements, and some of our servers suddenly moved to a closed network segment. The most revealing graphs disappeared, visualizations of the deformed grid vanished. Some letters disappeared retrospectively from the archives. The official line became this: minor discrepancies in the positions of faint stars are the result of systematic calibration errors and do not require special attention. Only we knew that errors cannot line up in perfect intersections at the same point in the sky. And yet, we were left with a small loophole. ALMA continued observing the region, formerly under other projects. Occasionally, we'd see rough data that hadn't been filtered. We continued to watch the beam play with the background, the stars continuing their slow, creeping motion. A year later, we began to notice new oddities. Now, not only stars, but also some distant quasars, sources that should be virtually motionless on such scales, were creeping. Their angular shifts were microscopic, but statistically significant, and all of them, those should have been motionless, eventually formed the same pattern, a slow convergence toward the regions where our beam was strongest. The picture was becoming more comprehensive. It no longer looked like a local defect. The behavior resembled a large, very slow swirl in the coordinate grid, with each object shifting slightly so that, when projected onto our sky, everything would converge on the line of 3i Atlas's future motion. One night, sitting in a dark office with only the monitor on, I caught myself with a very unpleasant thought. What if the comet is not flying through our system, but on the contrary, that our sector of space is being carefully moved to intersect with its path? This small difference in wording changes everything. In one case, we're dealing with a rock flying past our apartment. In the other, it's the house itself being imperceptibly shifted toward the rock's trajectory. During the same period, the first reports of strange glitches in other fields appeared. Several groups complained of small but persistent discrepancies in the measurements of constants, the speed of light, fine structure, even gravity. Everything was within experimental error, all within tolerance, but with an unsettling trend. If extrapolated forward, after a couple of decades, our familiar constants would begin to creep, just a little. At a closed seminar, a theorist drew a symbolic picture on the board. A small square, a local region of space, an arrow, the direction of the pulling force. If someone wants to tweak the structure on a large scale, he said. They'll have to slightly recalculate the local parameters. We were just unlucky enough to be inside the working region. We wanted to chalk it up to paranoia, but each new data packet from ALMA made that increasingly difficult. The beam didn't disappear. In fact, it seemed as if a sort of funnel was forming in the spectral space around it, an area where the background was slightly cooler, slightly smoother than in neighboring regions. It was as if the universe's radio noise was being gently cleaned out along its edges. One evening, while we were running simulations again, a junior graduate student suddenly asked, "If a comet is dragging the structure of space with it, we ourselves are inside that structure. Can we even see the real beam? Or is everything we see a distorted version?" No one answered, because the honest answer was, we don't know where the object ends and the background begins. By the time 3i Atlas's predicted encounter with our system was several years away, a strange ritual had taken hold among us. Once a week, we'd gather in a small conference room, close the doors, and open an old, unapproved visualization, a dynamic map in which the celestial sphere was drawn as living tissue, and our creeping stars, quasars, and radio beams were transformed into smooth lines. This map revealed something that wasn't in the raw numbers. Around the comet's future trajectory, the fabric of coordinates seemed to be beginning to contract, forming something like a slow-moving vortex. Not a classic gravitational one, but a geometric one, as if someone were changing the very way distances and angles were measured at this point. "Maybe we're misunderstanding the word comet altogether," one colleague once said. "We're seeing a small piece of the process and trying to describe it with outdated terms. But in reality, Atlas is simply a marker of where major work is currently taking place in our system." The word work sounded so casual that we all laughed nervously. Publicly, we continued to pretend everything was going according to plan. Articles talked about improved accuracy, new calibration methods, and observational prospects. Interviews talked about a unique opportunity to study an interstellar object. No one said out loud that it wasn't the object itself that scared us, but everything that was happening around its future position. Within the group, the fear grew exponentially. Too many independent systems, optics, radio, gravitational observations, neutrino detectors, were providing indirect hints that our corner of the universe was behaving strangely. Too many coincidences were pinned to the same direction. One night, I left the lab and looked up at the sky. Where we'd calculated the intersection point to be, there was nothing special. It was just an ordinary patch of black dome, with a couple of faint, unremarkable stars. I tried to imagine that behind that dark patch someone was holding the edge of our coordinate grid and slowly pulling it toward their trajectory. I suddenly found it very difficult to breathe. Not from the altitude, not from the cold, but from the feeling that we were not the center of the story, not even its heroes. We were just a piece of scenery, carefully rearranged backstage before the lead actor's entrance. When 3i Atlas finally enters our inner sanctum in a few years, news feeds will be filled with headlines about a rare visitor, an interstellar comet, and unique scientific data. People will watch beautiful animations of its gas and dust tail and listen to expert commentary on the composition of its ice and the object's origin. Few will realize that long before this arrival, faint stars had already begun to crawl across the sky, aligning themselves with its path. That ALMA had already captured a narrow radio beam, hanging in the void like an invisible tether. That some constants had already begun to shift slightly, adjusting to the new configuration. And even fewer will remember that once upon a time, a small group of astronomers in a dusty room tried to say, "It seems we're being pulled." But their voices dissolved into noise, the same as the radio noise of the universe, which someone, somewhere, may have long since learned to transcribe. Sometimes I want to believe that all of this is just a complex game of statistics, a projection of fears onto random fluctuations. But every time I open the latest data and see another faint star take a tiny step toward the same point, my stomach tightens. We're used to thinking we're studying the universe, but 3i Atlas and its invisible radio beam are teaching us something far more disturbing. Perhaps the universe is currently rebuilding us, and we're merely detecting tiny folds on the surface of a process whose scale extends far beyond our catalogs and sky maps. And somewhere out there, in the future, where the comet crosses the intersection of all these lines, the final answer will be given as to who we were all this time. Observers or cargo that was simply dragged closer to the working area. With less than 3 years remaining until the calculated node, the moment when 3i Atlas, in projection, would pass through the intersection of all our lines, the world, strangely enough, lived peacefully. Publicly, everything seemed predictable. Articles, reports, interviews, beautiful infographics, the usual mix of science and media fluff. Inside our private chats, however, the conversations grew increasingly tense. We had already stopped arguing about whether there is an effect and began arguing about what exactly is being deformed, the metric, the field, the constants themselves, or our understanding of measurements. The first alarm bell came not from the sky, but from orbit. Several navigation satellites experienced a brief but synchronous failure almost simultaneously. The official explanation was a software error, an update glitch, or interference from solar activity. But when we superimposed the timing of these errors on the 3i Atlas position map and the direction of the radio beam, the hair on our arms stood on end. Each failure occurred at the moment when the millimeter wave beam passed through the corresponding section of the celestial sphere above these satellites. It was as if a narrow signal, invisible in the normal radio spectrum, was carefully sweeping orbital space, brushing against our technological devices as it passed, not destroying or breaking them, but rather marking, calibrating, checking for a response. Pulse, pause, pulse, pause. The satellites twitched, their correcting thrusters fired without command, and the timestamps drifted off for a split second. Then everything returned to normal, and the engineering reports chalked it all up to anomalous noise. We tried to draw attention to this. We wrote a classified memorandum, collected statistics, and showed synchronization graphs. The response was short and icy. Correlation is not causation. Continue observations within the approved programs. Dissemination of unverified interpretations of the data is strictly prohibited. Translated from bureaucratic jargon, this meant, "We heard you, and we really don't like that you noticed." ALMA continued to observe the same region of the sky, although now access to the raw data had to be literally clawed out. Intermediate filters and automatic cleaners were introduced that discarded anomalous peaks as artifacts. We had to write our own parallel code that saved everything before deletion and output it to a separate unlicensed server. It was like a clandestine lab within a normal observatory. On the surface, we were doing mundane astrophysics, but at night we were cracking open the archives to see how that very beam was behaving. The closer we got to the estimated year, the clearer the picture we perceived became. The radio beam no longer appeared as a single stream. In the vicinity of the future Medri Atlas position, it began to fragment into many thin, almost parallel lines, forming something like a three-dimensional fan. Translated into understandable images, it seemed as if someone wasn't simply pulling a single hook, but was stitching our sector of space with a set of thin threads, gradually drawing them together into a common knot. Meanwhile, the optical maps were experiencing their own madness. The creeping stars hadn't stopped. Now new ones had joined them, even fainter, even further away, ones that had previously been hidden in the noise. The machine learning we trained to recognize these tiny shifts began automatically finding candidates, points whose forward extended trajectories intersected in the micro-neighborhood of that very knot. There were hundreds of them. The sky map began to resemble an image in which someone had gently pressed a finger into the center, and everything around it was slowly flowing toward the pit. We didn't know how to talk about it. Formally, it looked like a statistical anomaly in the catalogs, worthy of a dozen cautious papers and a couple of grants. In reality, it was like preparation for something we couldn't name. One of our team, tired, unshaven, with a feverish gleam in his eyes, once uttered a phrase that stuck in everyone's minds. Maybe we're not observing Atlas approaching. Maybe Atlas is adjusting space to observe us. About a year before the event, strange coincidences began to occur on Earth. Small, local, seemingly unrelated. One atomic clock station recorded a micro-frequency jump that conflicted with the international timescale. Elsewhere, an astrophysical detector detected a neutrino burst with no apparent source. In a third, a group of geophysicists noticed a tiny but synchronous change in gravimetric readings. When we compiled these cases into a single table and timestamped the beam phase and comet position, the coincidences formed a ladder. Each such instance occurred at moments when the millimeter beam in our data adjusted, as if checking how much the tissue had yielded in a particular spot. Usually, such things are called paranoia, but paranoia is when there is no data. We had numbers, graphs, maps, signals. They just didn't fit into the usual picture. In the usual picture, a comet is rock, ice, dust, chemical composition. In our picture, 3i Atlas looked like a moving boundary of a region, within which the parameters of space were being rewritten. Several months before closest approach, we were officially forbidden from discussing the comet outside of approved reports. Any internal communications were automatically copied to the monitoring center, using password-protected addresses. Several colleagues were suddenly transferred to other projects, officially at their own request. Access to some ALMA archives was temporarily restricted for maintenance. We realized we weren't so much being monitored as being sidelined, like children who accidentally stumbled upon an adult's plan. There was only one thing left to do: wait. The day we'd calculated as 0 began in a disgustingly ordinary way. Cloudy skies over the observatory, familiar incoming emails, new data from Gaia, where a couple dozen more faint points had made their tiny steps. The news on my phone reported everything but the comet. Publicly, 3i Atlas was a distant astronomical curiosity, no more noticeable than another exoplanet catalog. No one had said that today, its projection in the sky would pass through the very point toward which our stars had been crawling for years. A few hours before, we received the last gray data packet from ALMA, unsigned, without an official route, just a file in a secure channel with the sender identifying themselves with a single letter. It contained a series of spectra taken with insane temporal resolution, tens of thousands of measurements per second, tightly focused on that exact region of the sky. We loaded the file, launched the visualization, and saw the radio beam cease to be a beam. Instead of a single crowded spectrum line, the screen was filled with dozens of thin bands, rhythmically flickering, intertwining, and forming strange patterns. If you look at it as noise, you'll go crazy. If you try to see the structure, you'll go crazy even faster. One of our guys wrote a script that interpreted signal intensity as brightness and frequency as the position of a point on a plane. A few seconds later, a slowly flowing diagram appeared on the screen, something between a field map and a technorganic drawing. At the very center, where all the lines converged, a figure emerged, resembling an idealized funnel, a surface descending to a point, pulsating in time with the flashes. And at the same moment when the intensity in the center reached its maximum, the light in the room went out. This wasn't a simple power outage. All the devices were still working, monitors glowed softly, servers hummed, backup power was normal. But the most important thing was gone: communication from the outside. The internet, the communication lines, even the mobile network, everything went down in the same second. The local network was alive, the global network was dead. We were like an island, cut off from the rest of the world. Outside, the sky remained just as gray. No flashes, no gunshots, no Hollywood-esque sky portals. If it weren't for our charts and the ringing silence on the comms, no one would have guessed that something was happening. Over the next few minutes, we did everything we could. We checked the equipment, activated backup lines, knocked on the doors of neighboring observatories. No answer. It seemed as if the world had simply been switched off and put into flight mode. Only two things continued to update on the local network: our receiver readings and our internal clocks. Both were behaving too perfectly. No noise peaks, no random drifts. For the first time, our data looked like it was being plotted not by a real instrument, but by a careful theorist. When the connection returned, only 15 minutes had passed, but those 15 minutes felt drawn out, viscous, as if time inside the observatory had lagged slightly behind the outside. On the stand with the world time minute markers, our watches showed a delay of a few milliseconds. It seemed like nothing, less than the blink of an eye, but for a system synchronized by atomic clocks, it was too much. At the same time, strange reports began arriving around the world. Somewhere, the power went out for a split second. Somewhere, radio stations went silent. Somewhere, GPS gave logisticians directions through non-existent streets. In hospitals, life support monitors flashed a single dead frame, with all the lines instantly straightening. All of this was attributed to an avalanche of minor infrastructure failures. However, in our table, next to each of these episodes, there was the same timestamp, the very same interval when ALMA showed the maximum peak in the center of the funnel. Meanwhile, 3i Atlas simply orbited. Through the telescopes, it looked exactly as it should, dim, barely noticeable, with a subtle hint of activity. Its position matched the calculated one. It behaved exemplarily. If you were an amateur astronomer with a small telescope, you would sigh in disappointment. No miracle, just another chunk of ice flickering on the periphery of your attention. The reports released months later were sparse and meticulous. During 3i Atlas's passage through the inner solar system orbit, short-term anomalies in the operation of infrastructure systems were recorded. Minor discrepancies in high-precision clock readings were observed. A causal relationship with the astronomical event has not been established. There was no mention of crawling stars. No mention of a radio beam either. ALMA officially reported that no stable, narrowly focused sources other than those known were detected during observations. Our rough plots had disappeared. The file with the last visualization of the funnel was empty when I tried to open it. Zero size, a blank memory block. Sometimes I think we've truly lost our minds in the face of a mundane cosmic event, that the beam was an artifact, the shifts a mathematical aberration, and the 15 minutes without communication a banal man-made accident. It's easier to live like that. It allows us to continue looking at the sky and pretending that everything there still obeys the same laws as in textbooks. But every time I open the latest catalogs, I feel the same icy heaviness in my ribs, because the stars haven't stopped moving. Only now their trajectories don't converge on a single point but diverge from it, like the center of a ripple on a pond that someone has already disturbed. It's as if someone pulled and dragged our section of space towards 3i Atlas, did what they wanted, and now is letting go a little. In its new modes, ALMA sees a different background, slightly smoother, slightly quieter, as if some of the cosmic noise has migrated elsewhere. The constants in the latest experiments still fit within the tabulated values, but strange tails flicker in the tails of the distributions. Gravitational detectors sometimes detect the faintest oscillations that don't correspond to either black holes or neutron stars. Official science will continue to claim for a long time that this is simply a new level of sensitivity and statistics, and it will be right, in its own language. We really have begun to see things we couldn't see before. The only question is whether our eyes have changed, or what we're looking at has changed. 3i Atlas is long gone. It's now somewhere out there, beyond the orbits of the giants, continuing its journey into the darkness. Press releases barely mention it. It's become a catalog entry, further confirmation that interstellar visitors do exist and are probably not so rare. Only for a small group of people who once sat in a dusty room in front of monitors with crawling stars. This is more than just a visitor. For us, 3i Atlas is a mark on the scale, a line after which our sector of the universe became slightly different. Sometimes, at night, I go outside, look at the sky, and catch myself with the strange sensation that the picture has become a little more smooth. It's as if someone tightened the mesh, smoothed out the wrinkles, cleaned out the noise. Beautiful, perfect, almost too perfect. And in moments like these, I think that somewhere out there beyond our understanding exist beings or processes for which our galaxy is simply a piece of material in a vast workshop. 3i Atlas, a radio beam, creeping stars, 15 minutes of silence, these are just tick marks in their workbook. Adjusted, calibrated, recalibrated. We wrote it differently. Anomalies not confirmed, systems operating normally. And yet, every time I see a new sky map, I have an uncontrollable urge to check. Have any of the faintest stars started creeping again? This time, somewhere else? Because if they do, it means our repair wasn't the last one. And then 3i Atlas won't be a unique comet, but just the first marker in a long series of works no one is going to ask us about.